Hello everybody, welcome to the next video in the series of creating our own library for handling sockets. In this video we are going to implement our advanced TCP connection manager. With it we'll be able to manage multiple TCP connections, open listening sockets and handle communication efficiently, sending and receiving data on any of those connections. At the top I've defined a base abstract class called connection. This class provides a few essential methods like write, start reading data and stop. It also exposes a new data arise signal which is triggered whenever data is received on the connection. The base class is designed to be reusable for any type of connection, TCP connection, HTTP connection, or even WebSocket connection. And in the destructor, I make sure all slots are disconnected from the signal so no dangling connections remain. Next, we have the TCP connection class, which inherits from connection and represents a single TCP connection. It overrides the methods of the base class and stores a TCP info object. The TCP info structure holds all the socket details, IP, port, and protocol, TCP or UDP. In other words, it's the metadata that uniquely defines the socket. The TCP connection itself maintains a reference to the TCP connection manager and works through it all for all operations. Essentially, anything that happens on a connection, sending, receiving, or starting to read data flows through the connection manager. Now let's move on to the main class of this project, and actually the backbone for the future HTTP and WebSocket layers as well, the TCP connection manager. This class is responsible for anything related to connections, opening and closing sockets, creating listening sockets, handling incoming connections, starting data reads, and managing threads for each of the connections. For signaling, I'm currently using boost signals, although I also implemented a custom signal for my own use case. In fact, boost wasn't strictly necessary here. I could have built something lightweight with STD function, but for now I will stick with boost. At the top of the header, I defined a small targeted signals helper class. The idea is that when the connection manager is handling multiple servers, each listening socket should be notified of its incoming connections independently. This allows each server to handle its own clients. The TCP connection manager exposes three key signals. New connection, triggered whenever a new connection is established. Connection closed, triggered when a connection is closed. New connection on listening socket, a targeted signal that alerts only the specific listening socket about a new connection. There is also a DNS lookup function. Not currently in use, but I built it earlier and may need it later for the HTTP project. The class provides two open connection functions, while delegating to the other for connecting to a given address and port. Essentially, these open a socket to the target host. The write function takes a TCP info object, which is, as you know, represents a socket address, port, and protocol, and a message string, then writes that message to the socket. One of the most important methods is open listen socket, which starts a listening socket for incoming connections. In addition to these, there are several helper functions, retrieving a weak pointer to a connection, starting data reads, or closing connections. Private functions are used internally to be called and run from a different thread. As for members, the class maintains multiple synchronization mechanisms, a dedicated cleaning thread, and two hash maps to keep track of connections and connection threads, all ensuring the manager always knows what's happening with each connection. I moved the helper functions we discussed in the blocking TCP video, make socketDDR, which creates the IPv4 or IPv6 socketDDR objects and print error message, into this TCP utility header to keep things organized. The TCP server class holds a reference to the TCP connection manager so it can connect to its signals. It also stores the listening socket and a set of all active connections. The constructor only sets up the reference, and once the start method is called, the server creates its listening socket and connects to the two manager signals: new connection on listening socket and connection close. The server keeps track of its own connections and provides a broadcast method to send messages to all of them at once. Now let's move on to the CPP files, starting with the most complex one, the TCP connection manager. We started by including the necessary headers. First, let's look at the constructor of TCP connection manager. Since this class is responsible for managing all TCP connections, and no connection can exist without it, the constructor begins by calling WSA startup to initialize WinSock. If initialization fails, we log the error and exit early. Once WinSock is set up, we launch a dedicated cleaner thread. This thread continuously monitors for finished reading threads, and whenever it detects one, it safely removes it from the manager's internal map. This ensures the resources from close connections are cleaned up. Next, we define the destructor of TCP connection manager. When the manager is destroyed, we clean up everything properly. First, we call the stop function, which stops the internal connection threads and closes all connections. After we stop all threads, we make sure to wake up the cleaning thread one last time to be sure it noticed the stop as well. All connected signal slots, new connection and connection closed, are disconnected. Finally, we call WSA cleanup to release WinSock resources. This ensures that when the object goes out of scope, no background threads are left running and the networking stack is properly cleaned up. Now forward to the open connection functions. They open a TCP socket to the destination address and port. Optionally, it binds the socket to the source address and port so the connection uses a fixed local IP port handy when firewalls NAT require a specific source port, otherwise the OS picks one for us. We start by creating the socket. If a source IP port is provided, we also set SO reuse ADDR to allow faster binding after a block closes and bind to the source. For clients that don't bind a local port, SO reuse ADDR generally doesn't matter since another ephemeral port can be used. You can bind to a source address port to take control of connection identity instead of letting the kernel decide automatically. We also build the destination and source SOC ADDR objects if we have. We call the connect function to connect to the destination. We then create the TCP con-info, which is the file descriptor peer IPM port object, which is actually the socket object, and then construct a TCP connection as a shared pointer and immediately start reading data from it by default. We store the new connection in the connections hash map keyed by the socket file descriptor and log the new connection. I now use a blocking connect as previous non-blocking attempts cause hard to trace bugs, for example when sending an HTTP request to Google. Even though start reading data is called on the connection, the actual work is delegated back to the TCP connection manager since this is the component that knows how to handle it. The manager first checks whether a reading thread already exists. If not, it spawns a new thread dedicated to reading data from the socket. We use a log guard here because the cleanup thread also needs safe access to the same map of connection threads. Once the reading thread finishes executing read data from socket, it calls connection function to handle proper cleanup. The whole logic of reading data from a socket happens in the read data from socket function. We wait for the socket activity using WSA poll with a timeout of 2 seconds. If there is activity on the socket, WSA poll will return the value bigger than 0. We call the regv function to receive the data. As discussed also for the other project, regv function returns the number of bytes received. If we read something, we can optionally log it for debug, locate the owning connection. If it was already removed, we exit the loop and fire its new data array signal with the payload. If regv function returns the value 0, it means that the socket was closed by the peer. Remember, there was an activity on the socket but nothing received, so the socket was closed by the other part. If the WSA poll function returns the value 0, it means that the timeout expired. As such, we simply go back to waiting again. If there is any other value, it is an error, we log it and exit the loop. In a nutshell, the read loop runs until the connection is closed by other side or the manager is stopped. As we saw in the previous start reading data function, after the loop exits, closecon function is called to do the cleanup. Closecon function deletes the connection from the map, calls the signal that the connection is closed, and using the condition variable, it wakes up the connection threads cleaner to delete the connection thread. This workflow is necessary to ensure that everything closes and is properly removed. We've reached the core function of the TCP connection manager, open listen socket, the one that actually lets us run a TCP server. It takes a host address and a port, and as the name suggests, it opens a listening socket for incoming connections. Here's the flow. First, we call the socket function to create the listening socket. Unlike earlier examples, we set this socket to non-blocking mode. On Windows, that's done with IOCTL socket function. We're using the FIONBO function option. On Unix, you'd use the FCNTL with O non-block option. Next, we set the SO reuse ADDR option. This allows the OS to quickly reuse the address if the server restarts, which helps us minimize downtime. It is a server-side function, so this is important. Then we prepare a SOC ADDR start with the chosen IP endpoint and bind the socket to them. If everything succeeds until now, we call the listen function. The second argument to listen sets the backlog size, the number of pending connections the OS can queue before new ones start getting refused or dropped. Finally, we wrap everything in a TCP con-info object that created the TCP connection shared pointer and launch a dedicated thread to monitor and accept incoming connections. The check for connections function is more or less similar to the read data from socket function. It is done in the following way. We use an FD-set structure, which lets us check sockets for events such as readability. We create the FD-set and add our listening socket to it. We then check for activity using the select function and give it a 2 seconds timeout. If there is no activity, a value equal to 0, we continue and loop back to wait again. If there is activity on the socket checked using FD-is-set, it means that the client is trying to connect. At that point, we call accept, which gives us the details of the new connection inside the SOC ADDR object. We create the TCP connection, start reading data, and then we add it to the connections map. We also trigger here the targeted signal so the TCP server linked to this listening socket knows a new connection is available. Another function that we have is the write function, which handles sending messages through the socket. First, we verify that the connection is still valid. Then, we attempt to send the data. If sending fails, the function returns false, signaling the TCP connection that the connection is faulty and may need to be closed. Finally, we also define the helper private functions to access the connection's hash map in a thread-safe way. This is added later on, where I decided to talk nonetheless about the DNS lookup function, although currently we are not going to use it. We are going to need it in the next step when we will send HTTP requests to actual servers, but until then it is not needed. We will store the IP address in a char buffer. Lifetime extension is applied. It is okay to define it like this here. We then create a struct ADDR info where we specify what we are looking for. In this case, either IPv4 or IPv6 and TCP. Remember the sock stream, called hints. Afterwards, passing the info stored in the ADDR info struct, we get back a linked list of addresses as sock ADDR structs. I don't need to iterate for the whole linked list because I asked only for one type, IPv4 or IPv6 and TCP. Using inet and top, we convert the ADDR in sock ADDR struct from binary format to human readable. It is the opposite of inet Python used in Meg sock ADDR that converted human readable to binary format. In the end, and this is really important, we have to free the memory for the linked list. As mentioned also in the beginning, the TCP connection doesn't do the heavy lifting itself. It delegates all of its work to the TCP connection manager. Now to the main function. We start off with a printing function that we will connect later to a signal to be able to see data received. I create a handler and two servers, both on the local host, one on port 12301 and the other one on port 12302. I create a hash map to store the connections. To the new connection signal of the TCP connection manager, I attach a function that is triggered once the new connection is created. In that function, we take the weak pointer, see if the connection is still valid, and we store it as well in our main function. Within the lambda passed to the signal, we also connect the printing function to the new data arrived signal of the TCP connection. To the connection's closed signal, we add the function that removes the signal from our connection's hash map. Afterwards, I start to producing threads for each server that broadcast a message for their respective clients every 5 seconds. Let us also open a client that connects to the first server in this app as well. It sends only 5 messages in the beginning to the server every second. We then wait for the Q key to be pressed on the main thread. Once that is pressed, we broadcast messages that we are going to close the connection. We stop the broadcasting threads, stop and clear the connections, and stop the handler. This is the whole functionality of the non-blocking TCP communicator that would be the base for any high-performing application. There are tons of improvements still to be made, but this is a good working version that provides us the functionality that we need for the upcoming projects. Let's test this. So I start the application, I get that the WinSock is initialized, I get 2 listening sockets because we have 2 servers, and 1 connection from the client that we just created in this application through the server, and also 1 from the server to the client. I can also test it using the JavaScript application that we created in the last video, so node TCP test. I can enter a message here, hello, how are you? I received a message from the server in between, because the server is continuously broadcasting to the clients. I can close the client connection. I can connect to it again. I get the connection. I get on the server side that the connection has been closed. I get a new connection. I can close this again, like that. And then if I keep this connection open and I press the Q key on the main application that we just wrote, then I get that the connection is closed on all of the applications. The reason that it takes a little bit longer is that on the server producing threads, we wait every 5 seconds to send the message, and the thread sleeps here. Once we request the stop, it takes 5 seconds to notice the stop. And once that happens, everything is closed up, cleaned up, and yeah, we finalize everything. As a final point, I wanted to test with AI and ask Cursor to create a comprehensive list of tests for what we've done until now. And this is what we actually have now. So let's see together what it created, and let's see what happens here. So basically, I will just go through unit tests _TCP. We can also go through the performance tests. So basically, it has this unit test framework where it has an assert true and assert equals. That's interesting. Yeah, I don't know why it does this with the static atomics. It started by testing the targeted signal class. Oh, that's nice and interesting. So basically it's created 3 sockets, it connected to the signal, and then it tried to call them. Oh, wow, nice. Then it went to test the TCP con info. That's nice to also have tests for that. Then it tried to test the invalid operations, so which are like, connecting to an invalid socket, trying to get the connection, but there is none because, it's an invalid socket, and again, trying to create an invalid connection. Some tests for the DNS function. I'm not sure if these work correctly. Source binding, which is like creating a listen socket and testing that this listen socket works fine. Rapid cycles. What does it do here? It has 20 cycles, it opens the connection, it tries to get the connection and then it stops it. So basically it's like a stress test. Resource cleanup, I'm not sure if it can do that properly. So it has the manager here, manager stop, give it time to clean up. Yeah, but yes, that is nice, but you need access. Maybe I would do this in an own class and test it together to see that, yeah, as a friend class of the TCP connection manager, to see, hey, I stopped this, I want to see if all the objects are cleared. Test port edge cases, should auto assign, hide port number, privilege port, likely to fail, okay, that's nice. IP versioning, data integrity, I don't know, testing data integrity under load. It connects, it tries to find the message. Oh yeah, so it basically checks the number of messages received and the number of correct messages, and there is the success rate. Server lifecycle and connections. Oh, it's done interesting things, but although I'm not sure that all of these are relevant, like we saw earlier. The thread management, verify correct number of threads created and cleaned up, but how does it check? Because again, it's not a friend class, so you create multiple clients, close connections one by one, okay, that's cool, but yeah, you don't know. Thread management test completed without crashes, so basically if it doesn't crash, but it doesn't know that the threads have been actually stopped. But that's good because already you have multiple clients with multiple servers trying to connect. So yeah, there are tons of synchronization mechanisms that should go. And to be honest, it found some bugs in my code. Verify connection is immediately in the map, but how does it do that? Yeah, it doesn't have access to this. So this code, this is more or less the first version. Although it found some things, there is still a lot of room for potential improvements. Let's see how this works. I have to go back to this one, and where is it? I think here. Unit tests, and if I run those now, so the target signal is okay, the TCP con, yeah, it's perfect. Invalid operations, so get connection invalid, arcade exception, expected test, unit test failed, so some tests failed for the DNS lookup function. We should improve that if we want to work with it later. It already went past it. It opens and closes connection, so there's a lot of threading mechanisms. If something goes bad during the synchronization, something would fail here. Connection map integrity. Oh wow, there's a lot of things that it's running, and it's really funny. I would do a little bit of improvement here. Maybe I will come back to it later. But what I would do, I'll tell it to use the Google benchmark framework, and first of all, and second of all, I would tell it to improve the tests, because some of them are quite good, but some of them are not testing anything. So you don't test thread management until you see that there are actually no longer thread stuff there. You cannot test memory leak without having access to the internal things of the class. So it needs to be a friend class for the TCP connection manager to be able to test it all together. But I will do that, and I will try to improve it. As you can see, past 148, failed 2 were the DNS ones. Although we're not testing anything. The tests that we actually have until now are passing. So that's quite nice and good. Thank you for watching to the end, and I hope you find this project cool as well. As you can see, this is already in a working state to be a messaging app, for example. It is already the good base support for different protocols to be added on top of it. As usual, please leave in the comments what you liked in this video or how it can be improved. Don't forget to like and subscribe. I will go further with this challenge in the next video. Thank you very much again, and see you in the next one.